All right, so like I said, it's Wednesday, it's 10 a.m. It's time to learn some chemistry. Now, if you remember last time, what we were talking about was we were discussing atoms. And we talked about quite a few different things about atoms. And we talked about the periodic table, subatomic particles, and subatomic particles. And this is all really good stuff to learn about and kind of a firm foundation for when we begin talking about chemical reactions. Now, before we get into that, and as we kind of continue in this conversation about like atoms and subatomic particles, what we need to get after and what we need to learn about are referred to as scientific laws. Now, these are all things that you've probably been exposed to a little bit previously, and you've maybe heard or thought about them, but we're going to kind of put some details to it. So, looking at these two pictures, we've got a before and an after picture. Go ahead and anyone, if they'd like to, add something that they notice about, well, about the two pictures. You can compare them or just say anything about them, really. I've got one comment that it's the same. You're referencing the mass. The weight did not change. You're absolutely right. But did the contents of either of these two pieces of glassware change? Yes, absolutely. Now, the pieces of glassware that we have here, we've got this guy right here, which is known as an Erlenmeyer flask. Erlenmeyer flask. Then we've got a grad cylinder, which I'm just going to label as graduated cylinder. And, there's a couple of details that we can throw at this. First of all, the solution level in the graduated cylinder, it looks like it's nearly at its capacity. And I see 25 right here. So I'm going to go ahead and operate under the idea that this is 25 milliliters. Then I'm looking at the after reaction. I'm looking at the graduated cylinder and I see that, oh, well, my solution level here is at approximately 75 milliliters. Okay. So that to me indicates that this solution, this clear solution here, there's about 50 milliliters. I'm going to write that on the white part so it's a little bit better, more contrasting. 50 milliliters of solution. So I got 50 milliliters of this clear solution. I add this amber colored solution, 25 milliliters of it, and then I get this mixture right here that results. That's kind of a darker red, like a copper colored solution. Total volume here is 75 milliliters, so 50 plus 25. So my volume didn't change. In addition to that, my mass didn't change. So this is kind of interesting because was there a change between the before picture and the after picture? Yeah, people have highlighted that the color of this solution changed. So some sort of reaction took place, but that didn't result in a change in mass. That it changed maybe the contents, the composition of the contents? Yeah, probably. Do we know what those are? Not necessarily at the moment, but the important part about this is the mass didn't change. And so another way to put that is the mass was conserved. So the mass didn't change, the mass was conserved. Now, this brings us to a law known as the law of conservation of mass. And at the heart of the law of conservation of mass is this idea that matter is neither created nor destroyed during a chemical reaction. And to illustrate that, here's another example. Here what we have is 100 grams of a compound known as mercuric acid or mercuric oxide. So this is a compound made up of mercury, which on the periodic table, mercury is Hg, and oxygen, which I believe this is Hg2O. So when you take mercuric oxide and you expose it to heat, which is what's being done here, where we put a Bunsen burner, and we basically expose it to this high heat, what happens is this substance it undergoes a chemical change. It undergoes a chemical change because this oxygen is released as a gas. Notice how this is an open container, or this is not an open container. This is a open test tube. The oxygen's going to dissipate. The oxygen that makes up this compound, it will be released as a gas. The mercury, however, stays behind and continues to exist as a solid. The total mass of that mercury is about 92.6. And the total mass of the oxygen, which oxygen as a gas does have mass to it, is 7.39. Now, if we take 92.6 and 7.39, what's our total mass there when we combine those two? Basically, what's 92.61 plus 7.39? 100. So 100 grams. All of that mercuric oxide burns. And one fraction of it stays behind as mercury, and the other fraction stays behind as oxygen, or exists as oxygen. Now, that's what we have there for a ratio. Let's imagine, however, that we use 200 grams of mercuric oxide. If we did the exact same thing, but we increase the amount, what's going to happen to the mercury? And what's going to happen to the oxygen? We're going to have more of each of them. This scales up and it scales down. And it's like this perfect ratio, which is fundamental to a compound. A compound has a perfect ratio of different substances reacting, or different substances coming together. Much like H2O. Well, a water molecule is always going to be one oxygen and two hydrogens. If you have something other than two hydrogens and one oxygen, you don't have water. So this is the law of conservation of mass. This reaction takes place, but the mass doesn't disappear. The only thing that changes about this substance is it might convert into some other kind of material or some other state. Okay. Now, an example of this would be something that maybe you've done before, and that would be your science fair volcano, where you get baking soda and vinegar. The mass of baking soda that you use plus mass of vinegar. What that is ultimately going to equal is the mass of the water that results and carbon dioxide. So when this reaction takes place, you have two reactants, and in this case, you have two products, and the mass of this combined is going to be equal to the mass of these products that are combined. No mass is destroyed, no mass is created, nothing's lost or gained. Instead, they just kind of change into, or they undergo convergence into different substances. Okay, so then what we have in addition to that is we have laws of chemical combination. We have our conservation of mass, where this is demonstrating we've got two copies of one substance. So I'll label this as, these are both molecules of a compound that react with this other molecule of a different compound. What happens is all of those atoms that make up those two compounds basically just kind of get thrown into a blender and a chemical reaction takes place. And we end up with this right here. I always like to look at this and just say, okay, I've got two white, and that would be 4 orange. Well, that was my input. And what about my output? Well, I got 2 white and 4 orange. They've rearranged and they're in different substance in a different ratio, but that's what's happened. Now, another important law to understand is known as the law of definite proportions. What this law is basically what I talked about a moment ago. Water. Water has a definition. Water is 2 hydrogens and 1 oxygen. Now, I'm going to write a formula right next. I'm going to write a formula right here and put a thumbs up if I've written the formula for water and a thumbs down if I've written the formula for something other than water. Thumbs up if I've written water and thumbs down if I've written something other than water. Perfect. Lots of thumbs downs I'm seeing. That's fantastic because you're absolutely right. This is tempting because you see H2O, but you actually don't see H2O because it's H2O2. Now, H2O2 is hydrogen peroxide. This is a different substance. So that is not water. Water has a definition. Every compound has a definition. Aspirin has a definition for the number of carbons, hydrogens, and every other atom that's in there. Now, with that said, however, there's also a law of multiple proportions, where this kind of gives us the, I guess, context, or it gives us a sense of, well, oxygen and hydrogen are 2 atoms, and what they can do is they can combine with one another and make different substances. So with oxygen and hydrogen, you could make H2O. You could make H2O2. These are 2 examples of the pairings of otherwise identical atoms, or otherwise similar atoms. Oxygen and hydrogen, they can pair up in different ways. They could also make hydroxide. There's water, there's hydrogen peroxide, there's hydroxide. These are all different compounds, but they're both made with hydrogen and oxygen. Similarly, CO2. One of these we exhale because we're burning sugars and we're consuming carbon-based substances. And the other one is very fatal, and you have to be very cautious of it. So this is carbon monoxide and carbon dioxide. These 2 substances are both carbons and oxygens. The multiple proportions are the different ratios. So another way to put this is different ratios. So we have all these laws that define different substances. There's the law of conservation of mass. So your input and your output, the total mass is never going to change. Now, when we look back at this right here, and we look at the solid mercuric oxide, that's going to occupy different space or a different space than, say, the mercury alone. Well, the biggest difference is that this is mercuric oxide compared to pure mercury. So we conserve masses. Other variables might change, like volume, or the volume might change, but that's because you're undergoing a change in that substance. Now, other components are definite proportions. When we have a compound that has a specific ratio of elements to one another, of atoms to one another, H2O is water, H2O2 is not water. Which is why if we see something like there are substances known as diatomic elements, so O2 is a diatomic element. This is commonly known as oxygen gas. That's the type of, that's the state of oxygen that you inhale on a regular basis. Now, this is a little bit tricky, but I want you to answer, or my question is, and put into the chat a thumbs down or a thumbs up. The thumbs up is, does H2O2 have oxygen gas? Or the thumbs up would be yes, it does. And the thumbs down would be no, it does not. So does H2O2 have oxygen gas? Thumbs up for yes and thumbs down for no, it does not. Okay, I've got one thumbs down, lots of thumbs ups. Okay. So this ultimately, the correct answer is no, it does not. And I'm going to go ahead and do some erasing here to give you a little bit more space to see what I'm talking about. This ultimately has to do with how these atoms are arranged in space. So O2 looks like this. And I'm going to, this is, or these are 2 electrons. Then H2O2 looks like this. And this is tricky because this is a subtle difference. But one of the things that is worth noting is that this molecule right here has a double bond between these 2 oxygens. This one does not. So H2O2 does not have oxygen gas. It's a different compound, or it's a different substance with a different set of atoms present. So this is where it's kind of easy to fall into a trap. Now, another example, let me ask a similar question. H2 is hydrogen gas. Gas. It starts with a B and G. Hydrogen gas is extremely flammable. Does H2O have hydrogen gas? Thumbs up if yes, and a thumbs down if no. I got 1 vote for down. Another. I'm trying to keep my best poker face on. Okay, I got 2 thumbs up yes, or 1 yes. Okay, the correct answer is no, it does not. That's one reason. That's a great answer. It does not, I mean, that's an important thing to think about, a property of it. Water isn't flammable. H2 gas is flammable. But this also goes back to, and I know this this isn't really a part of what we've discussed yet, but this is where we're going, is the structure and the organization of these atoms in space. So H2 looks like that. H2O looks like this. Now, I didn't expect you to know that as the justification, but whenever I show you something like H2O2 versus H2 and O2, just because we have this letter and this subscript doesn't mean that this has the chemical makeup of this. So these are definite proportions. And so whenever we introduce a new compound or something like that, I'll give you a formula. I'll say C6H6O6 or something like that. That is a compound with 6 carbons, 6 hydrogens, and 6 oxygens. That is a different compound than, say, C6H6. So I just want you to be kind of aware of this moving forward. So that's definite proportions. Multiple proportions is really a look at, okay, we can have these different atoms and there can be different ratios. So ratios of atoms to one another. Now, let's look at a poll here. Just a second, I'm going to get the poll going. And this is going to simply be A, B, C, save. Go ahead and launch this one. The composition of water always yields 88% oxygen, 11% hydrogen by mass, which illustrates composition of mass, definite proportion, or multiple proportions. Give another 10 seconds or so to answer this question. Right, I'm going to go ahead and end my poll, and I'm going to share the results. Okay, so the winning answer was definite proportions. Second was conservation of mass. And third was multiple proportions. Okay, so this question had kind of a key word in it. Always. So the composition of water always yields this much oxygen, this much hydrogen by mass. So what's significant about that being it always does this is, and the use of the word water indicates that this is defined. This didn't say anything about, this water undergoes a transition or it undergoes a change. So key words that you want to look out for definite proportions would be something like identifying a substance. Oopsies. I'm going to stop sharing my poll results. Close that. Identifying a substance. If a substance is identified, then that should be a good indicator that, yeah, you're probably thinking about a definite proportion. Now, conservation. Anytime you're curious about conservation, you should be thinking about, well, is a reaction described / a change described. And then last but not least, law of multiple proportions would be something where you have different percentages. A substance is 20% oxygen and 80% carbon, or 30% oxygen and 70% carbon. So here we have different options that it could be. Okay, next up is this right here. So we've got another poll coming. And again, this is going to be an ABC poll. So okay, so there are 3 different oxides of iron. For a fixed mass of iron, the masses of oxygen and 3 oxides give a ratio of 6, 8, and 9. Now this defines something, but then it also throws a couple of key words here. Anyone can add to the chat, like this is a keyword that I notice and it stands out to me. There's one that I'm seeing that like, this is a really good indicator of what you should look for. Fixed, okay, okay. Different. 3 different, ooh. Interesting. Okay, I'm gonna give another 5 seconds. We got 50 people who have answered. Let's see if we can get it up to 60. So 93 people are here. We should be able to get 64 more. 3, 2, 1. 5, 4, 3, 2, 1. Okay, I'm gonna stop there. Share the results. Okay, so Jonathan just added to the chat 3 different. And that's really what I was looking for as the clues, as the key words in this question. There are 3 different oxides of iron. So an oxide is a type of a compound, but then more than anything else, there's 3 different versions of that. That gives us our correct answer of C, the law of multiple proportions. So that would be like 3 different proportions are indicated here. All right, now I'm going to stop the share. Close that. And then we're going to go on right here. So ultimately, what we've just kind of gone over is the simplification of what's known as Dalton's atomic theory. Now, the modern renditions or versions of Dalton's atomic theory is summarized here. Dalton assumed, and John Dalton is the name of this scientist, he assumed atoms to be indivisible, but atoms are actually divisible. What this means is that an atom is the simplest form of all matter, but there are subatomic particles. So that's a kind of correction to Dalton's idea. Next is Dalton assumed that all atoms of a given element were identical in all respects, including their mass. Now, with this, we know this is not true. And what we've got here as an explanation for this is something that we talked about last time. We talked about isotopes. Remember how we did that calculation where we said, okay, well, you know, if you get 10 Oreos or we got 100 Oreos and we put them all in a digital balance, those Oreos had different masses. That's going to happen. Is it still an Oreo? Yes, it is. Atoms are the same way. A hydrogen atom might have some variation or different isotopes of hydrogen have slightly different masses. Now, the third part of Dalton's atomic theory is that compounds are formed when atoms of different elements combine in fixed proportions. So this is really kind of a consensus. This is still agreed upon. And I believe that Dalton's theories were in the 1700s. And so this is basically the law of multiple proportions. And definite proportions. And then last but not least is that a chemical reaction involves a rearrangement of atoms, but there's no breaking, destroying, or creating of atoms. This is essentially, in a chemical reaction, you have the conservation of mass. So when a chemical reaction takes place, whatever mass was input is going to be the same mass that's output. Things might undergo conversions, and it might be oxygen might be liberated as a gas where it previously was not a gas, but that's essentially what we're looking at there. Okay, so that's all that I really wanted to cover today. We're ending a little bit early. I'm going to go ahead and stop the recording. And I did have, or before I stop the recording, I posted an announcement regarding the quizzes, specifically the Proctorio quiz. If you're still working on getting that sorted out, I hope that you have. If you ran into an issue with the Proctorio quiz, it was prompting you for an access code. I do not have an access code. I'm not going to provide you with an access code because Proctorio gives the access code. So if you're being prompted for an access code, that means Proctorio is not active, which means it could be a browser issue, it could be a computer issue. I gave you the info for contacting ITAC, itac@txstate.edu, or their phone number, which is 512-245-4822. So make sure that you get that resolved. I believe that I have that quiz closing this Friday at 11 p.m. If you please contact them, please, if you figure out what it was, or if they can help you diagnose the issue, please email me and say, hey, I had trouble with Proctorio, but here's how I got it to work. Let me know so that I can add that to our Canvas page so that if other people run into similar problems, they can resolve it that way. But it's not on Apple, it's on Microsoft. I had to do mine on a Microsoft laptop. Interesting. So Proctorio is something that, yeah, it's a piece of software, and yeah, I think that it's best if you use Google Chrome, which I think you can get Chrome on a Mac. But anyway, find out whatever it is that, or let me know whatever it is that you used and did to resolve your issues with it, and let me know. I'd appreciate that so then I can share it with other people. On my Mac, I had to follow the link and block ads, other components Mac allows in a browser. Okay, so it can work on a Mac, but okay, well, I'm going to go ahead and stop my recording.